Welcome back, everyone, to the second session today. And this last session of this mini conference is devoted to one of my favorite topics, particle heating and acceleration in jets produced by black holes and in charge gaps present near or far from the event horizon of a black hole. And this is a very important topic because particle heating in general determines how these accretion flows and jets look like and how they vary. So this will be our final presentation today. And this presentation is given by Alex Chen from Colorado University in Boulder. Alex, I'll give it to you.
Okay, thanks. Thanks for the introduction, and thanks for having me here. The talks were great and discussions were really nice. I'm going to tell you a little bit about gaps, like Monica said. This is a project done with Yaji, mostly with Yaji Yuan. She's my wife. This is actually the project that brought us together, so this will be this will always have a special place in my heart. So let me start with why we care. There are two motivations. One of them theoretical. For most of the people who are doing GRNHD simulations in the audience, this is probably a well-known problem. In the funnel, it's almost always density floored. So the code is providing the plasma in the funnel because the gas in the disk cannot penetrate into the funnel. And the funnel, no matter of the funnel, in a funnel will either plunge into the black hole or go out. So you have to keep replenishing it. So for radiatively efficient disks, they can usually produce a very bright radiation and some in X-rays to pair and annihilate to annihilate and create pairs in the funnel. But for low luminosity AGNs, very especially like M87 and Sgr A, that may not be an option. This is a plot from Monica's paper back in 2011. It's a very great paper studying this radiatively inefficient accretion flow. So they concluded that for M87, the drizzle, the X-ray photons from the disk is kind of enough to produce enough pairs in the funnel, but for Sagittarius A it's not enough. So in that case, a gap could show up somewhere in the funnel to produce the plasma. And the gap, basically what it does is that it induces parallel electric field, and parallel electric field is the most efficient way to accelerate particles. And the particles accelerated will emit gamma ray radiation, and that radiation can convert to pairs. There is also a theoretical, observational motivation. This is for M87, which interestingly Monica said in that earlier papers that M87 does not do this, but we will come back to that later. M87 show these TeV emissions are very variable. They vary on the timescale of RG over C, so it indicates that it comes very close to the horizon itself. So they observed M87 for many years, like these in 2005. This is the first time they show this. There's a Nature paper showing these flares. In 2008, there are quiet periods. There's also some flaring periods. In 2010, there's a huge flare that we call it. All of these vary like on the order of several RG over C. And on 2008, there's actually during these flares, there's also brightening of the core in X-ray and in radio as well. So there's another evidence that could potentially points to that the emission come from very close to the black hole. The gap is actually perfect for this in the sense that in order to produce pairs on the background soft photon field, the background soft photon field we know from M87, we just saw it with EHT is a millimeter. In order to produce pairs on that, you need TeV photons, and that is consistent with the kind of spectrum and the kind of photon energy gamma ray we see from 87. So, and the variability, the size can work as well because it's close to the black hole and the gap can be about RG over C as well. So this is just a picture I took from Jonathan McKean's paper. This is the funnel. Very simple drawing. My drawing of the gap will be somewhere here. That's what I'm talking about. Something happened here that produced parallel electric field that accelerate particles along the B field, creates emission, and produce pairs. So these are the questions we want to answer. So the first one is, I think it's pretty well known. I guess we more or less know when does it form. It forms when the plasma is not enough. There is a minimum charge density you need to sustain in the rotating magnetosphere. When you have a magnetic field, you rotate. If you don't have charge, you will induce parallel electric field. So that will accelerate particles. There's a minimum charge density you need to screen that. It's called Gorak-Julian charge density from pulsar magnetosphere. So we pretty much know the first question, but none of the others. Where is the gap? Is it steady or time dependent? What's the power dissipated? What's the radiation spectrum? How many pairs can it produce? If it's time dependent, what's the duty cycle? What's the time variability? Things like that. So these are the questions we wanted to address. So we did numerical simulations. This is the work, two papers from 2018 and 2019. The later published in 2020. So this is why I showed up 2020. But we took a force-free magnetosphere because in the funnel it's more or less force-free. Force-free basically means MHD, but you take the limit of mass inertia to 0. We start with some split monopole configuration. This is a color plot of the charge density that I was talking about, the Gorak-Julian charge density. It's negative here and positive here. There's some curious surface where it changes sign. It's called a null surface. We took one single flux tube in this magnetosphere. That's the white line here. We modeled the particles' motion along this flux tube. We found a pretty smart way to do this. This is essentially a 1D problem because particles are constrained to move. Yesterday we heard already Freya was talking about the scale separation. The gyro radius is so much smaller than the whole system size that they are basically constrained on the long B field. They do undergo E cross B drift, but you can identify that drift motion as the rotation or motion of the field line. So in that sense, it really is like the particles are beads on a wire on the moving field line. So that's what we took into account. We also take into account the soft photons. We assume a power law photon field around the black hole. It's uniform and isotropic, which is definitely an oversimplification. I'll come back to that. We model inverse Compton and gamma-gamma pair production along the speed field. So that part is pretty rigorous. We do Monte Carlo. And the peak part is also pretty rigorous. We do proper particle in cell in GR. The first paper was done with fake GR, and the second paper was done with proper GR. This is a movie. This is a very busy movie. I'll explain while running, but the first panel is basically the phase space of particles. There will be electrons, positrons, and photons. Electrons are blue, positrons are green, and photons are black. The green line is the electric field. I'll let it run for a moment. Initially, nothing happens. There's a huge noise in the in the electric field. It's relatively small. Once it develops, you can see that noise. It's very, very subdominant. This is the current density, the blue line. The orange line is the charge density. The dashed line in the middle is the background value. This is multiplicity down in the right-hand side corner. The bottom left is the spectrum of electrons and positrons and photons. Photons are in green. There's no photons in the beginning. So now you can see a gap opens. There's parallel electric field, which is huge compared to the oscillations. The gap size is about comparable to RG, like 1 point something RG. The particles are accelerated to pretty high Lorentz vectors, and they start to produce pairs. Photons. Photons are these black dots. And the photons start to convert to pairs with much lower energy, and then they start to screen the electric field. The electric field oscillates down to a very much smaller noise level. The particles and photon develop a power law. And when the gap opens, there's a bump in the very highest energy particles. That's the primary accelerated particles. Then those radiate their energy away into photons. Then the photon convert to pairs. We get very mild multiplicities. Multiplicity is the total plasma density over the minimum density, minimum being the Goldreich-Julian charge density. We get a factor of 20-ish. It depends on the parameter regime. Sometimes we get 50, sometimes we get 10, but it's always pretty mild. You don't get crazy multiplicities like 10 to the 5 in pulsar magnetospheres. So these particles, a lot of the photons you see, the black dots, do not convert in the box. They either fall into the black hole or escape outside the outer light surface. This dashed line here, where the electric field develops, that's the null surface. That's where the background charge density changes sign. And it seems unambiguously that the gap always develops here. So we ran this for about close to 100 RG over C. The recurrence timescale is about 10 times RG, and the gap size is about 1 RG. So we basically can answer almost all the questions I posed basically from these kind of simulations. Where's the gap? It's pretty unambiguously developing near the null surface. It is time dependent, so it's not static gap. It's recurring on a timescale comparable to RG over C, like a little bit longer than that, but the rise and fall timescale is RG over C. What's the dissipated power in spectrum? I'll show the spectrum later, but the power depends pretty much on the optical depth for both inverse Compton and photon scattering, photon pair production. Since both processes happen on the same background photon field, which is the millimeter photon field, so these actually have the very, very similar optical depths. So I'm just grouping them together. For EHT, implied soft photons flux, you can estimate a optical depth of about 500. In that case, the gap power is pretty small, actually. It's only 10 to the minus 4 of the jet power. It's actually not marginally lower than the kind of flare energies we see. But it scales with tau, roughly is tau inverse. So smaller optical depths, meaning lower density of background photon field, would enhance this power. The paramultiplicity, like I said, is pretty moderate. You cannot create a huge amount of plasma in this process. It will just create enough to screen everything, about 10 times more, but that's about it. That amount of plasma will not be able to produce any significant radio emission. So that's, and this is the power, gap power over time. We start with a very different initial conditions. So initially these spikes are the initial conditions, but it erases the initial condition and it becomes this very regularly recurring power output. This is not the light curve. This is just the gap power. The light curve is very likely more complicated because the radiation coming out will continuously change, dissipate, and convert to pairs, and those pairs will emit. So really, you need to integrate for for longer distance to get the real light curve. But the photon spectrum we measure at the outer surface of the simulation. Again, this probably will be modified if you follow them for a longer time. But at the outer edge of the simulation, the photon spectrum is a power law. Depends on where you, what time you measure it. There's this burst of photons during this burst of gap power. And those photons, when they come to the outer boundary, they look like this. So it's a harder power law. When there's not so much photons coming in, so when during those interims or quiescent times, then the photon is much softer. The energies here is rescaled, so it does not reflect the MHD energy, the M87 energies. If you rescale it to M87, this would correspond to about 20 or 30 TeV. So it's pretty consistent with what we see in experiments. So we see up to like 20 TeV, and then there's an exponential cutoff. So we back in 2018, we built a semi-analytic model to describe what is happening. We found a pretty simple scaling law for the parallel electric field, developing the gap. Depends on the B field, depends on the power law, the maximum energy, in the power law of soft photon distribution. This is the peak in the power law. This is alpha is the slope of the power law. The particles are strongly radiation loss dominated, so their Lorentz factors is a function of E parallel. So we have a scaling law for the Lorentz factors as well, and it agrees pretty well with the simulations. The dots are simulations. These are when the optical depth becomes pretty low, like 100 or even lower. It becomes it goes into Klein-Shiner regime where a lot of these cross sections are reduced. So this model works well when the optical depth is high. And it looks like for M87 the optical depth is pretty high. So I think for M87 we think this model should work. These are rescaled for M87. This dimensionless peak photon energy is at 10 to the minus 9. So the Lorentz factor can get up to 10 to the 7, it's somewhere here. But I think it should work pretty well for M87, and it give you reasonable estimates for the highest energy photon as well. There are several other similar works around this time. There's Emir and Benoit. They published this paper in 2018. They had also GR peak, but they did not parameterize this motion along B field. They just parameterized this motion along the radial direction. They don't have this effect on the B field. They didn't see a time-dependent gap. They saw a thermal bath of high-energy particles and high-energy photons. And the photons keep producing pairs. It's a steady power luminosity. But then this year, Emir and his other collaborators followed up on that paper. They ran a simulation for longer with the same setup. They actually recovered what we saw. So they see a time-dependent gap happening at the null surface. They have slightly different parameter regimes, and they also included curvature radiation. And interestingly, they concluded that curvature radiation is important for TeV emission, not inverse Compton. We didn't have curvature radiation, but we estimated power. It's different. So it probably is because it's a different regime. There's some work to be done there. And then Benoit and his student, they did 2D GR peak. They also found time-dependent gaps, but the gaps are very small in 2D. The gaps are not near the null surface. It's very close to the horizon in the near inner light surface. Yeah, so we don't have on the zeroth order, we agree with each other. We have a time-dependent gap that recurs over a very short time scale. But on details, we don't agree. So there's more there's more things to be done here. But overall, one of the things that is different for these models is that the soft photon field is different. So for the 2D GR peak, they use a modal energetic photon field, and it's not apparent what the photon, what the assumptions about the uniformness, the angular distribution of the photon field, and obviously the spectrum will matter. So that's actually one of the obvious next steps. I think this is something that should be understood. Ideally, it should be understood in the context of the GRNHD simulations that we have been running for M87. But moving back, we know pretty sure that the gap should be time dependent, but it always recurs. So this is not the kind of year-to-year variability that magic and has are seen. So there are quiet years, there are more bright years. No, this cannot be explained by this local thing. So we don't know what caused this long-term variability in the TeV emission, even if the gap itself is variable. And also there's this, what I said in the beginning is that Monica et al., they said that for M87 there should be no gap required. But that raises an interesting question. It can be interpreted in two ways. One is that, yes, you don't have a gap, so you need to find another mechanism that accelerate particles to TeVs and produce emission that we see. Or it could be that for most of the time, M87 is actually in the state where it can sustain this pair production from the disk photons. But there can be changes in the accretion flow on a timescale of several years that suppress this. At that time, there's a gap will emerge because of this. So this will provide an interesting way to couple this kind of high energy observations with what we can model using GRMHD on a much longer timescale. And I think this is a very interesting next step. So this is the long-term time variability I was talking about. This is the high energy SED of M87. So this is 2004, 2005, and 2008 and 2010. So you can see it's increasing over several years. And there's actually not on this plot, magic monitoring, keeps monitoring of M87. During 2012 and 2015, it comes down to a more quiescent state. So Jason has this, and his student was working on trying to model GR radiative MHD. So we're using this code eBlight. They can simulate GR MHD with photons and include synchrotron emission and self-absorption and Compton scattering. So they can produce a very nice synthetic spectrum from the GR simulations. So this is still a work in progress. I'm not going to explain this plot because this is not my specialty. Ask Jason if you have questions. But the goal, so I'm kind of involved because this very nicely gives you an estimate of the soft photon peak, as well as the soft photon spectrum and angular distribution anywhere in the simulation domain. That includes the funnel. So it gives you a very nice self-consistent, first of all, the magnetic field structure in the funnel, as well as the soft photon field distribution in the funnel. That is kind of what we were missing in our simple gap models. And this is, so that is why I was involved in trying to use these as information input to refine the gap models to make more concrete predictions. And another thing that will be interesting to explore will be long-term MHD evolution and how it could affect the luminosity in the gap. This is still work in progress, but hopefully can be done in the next several months. So I'll conclude I think gap is pretty promising emission mechanism, although it seems that to get the kind of flare energies, the gap is still a little bit low. The power from the gap is still a little bit low. The interplay between the gap, if there is one, the interplay of the gap with the accretion flow and the radiation from the accretion flow, I think it poses a very interesting question that can independently constrain some of the GR models, like sane and mad. I think that's something I would advocate that in the next few years we can all work together to improve our understanding of this horizon scale accretion. So yeah, that's my talk. Thanks.
Thank you very much, Alex. It was perfect timing. It's just the right time. So before people gather their thoughts to ask questions, please raise your hand. I would like to make a comment about my work from 2011. That work was basically focused on calculating the pair production in funnel using just one type of scenario, which was sane accretion disk. This was also done in 2 dimensions. So I'm afraid that these conclusions from that paper may not entirely apply to MAD or perhaps to different, particle heating ratio. So we have tried at that time, I think, only one options, with heating, a coupling ratio of electrons and ions in disk equals 3 or something like that.
Yes,
so, this conclusion from that paper was not very general, and I wouldn't say that, we don't have gaps in M87. We just have to really look at other different type of solutions, yeah? My work was just showing how to do it, and this calculation was incredibly hard, and now people looking at different options and different type of scenarios to actually check if we do need the gaps or not. All right, so there are questions. I can see Mitch Begelman, go ahead.
How do you think the jet gets loaded with particles? I mean, you said that the gap pair production was not enough to produce synchrotron radiation. There are some arguments that these relativistic jets are still dominated by pairs even quite far from the source. So presumably they have to be loaded by pairs at some point. And of course, it's a question of when the jet is first being accelerated. Is it drawing material from the accretion disk, which I think is disfavored by most people at the moment, or is it the pairs being produced in the jet in real time?
Yeah, unfortunately, I don't have a concrete answer to that question. It looks like from the gap alone, it will be very difficult to produce a high multiplicity for a very simple reason, because you create high energy photons and the secondary pairs on the same background photon field. So your high energy, your secondary pairs and the primary particles of primary photons will probably have very similar energies, like a factor of several difference. And that difference, so only that difference can go into the pair multiplicity. You don't get a very big energy separation between your primary and the secondary particles. I think that's a very general argument that disfavors the initially loading this jet with a lot of pairs, but I can't comment on what other mechanisms that can later introduce pairs. And also these photons will continuously go out and create pairs through other mechanisms. And, they will continuously create pairs. So I would relax this a little bit by saying that multiplicity can be 100, but yeah, other process probably.
Could I bring up an even more troublesome problem, or maybe it's a non-problem? There are some arguments that the accretion flow is entirely missing in M87. I mean, Blanford, for example, is saying that the discrepancy is so huge that you essentially have to have a vacuum magnetosphere confining the jet, and all the gas is way far out. So what do people think about that in this group?
It's an interesting proposition that needs to be explained in more detail.
Yes, so for example, is the model that you have shown, the wonderful movie with the gaps forming, that was scaled for M87? Did I understand that correctly?
No, this is in numerical in numerical units. So our philosophy was a little bit different from other groups, especially from Amir's work. They try to use realistic parameters. We try to downsample the scales so that we well resolve everything, the plasma physics, and we try to build up analytic model to tell us how everything scale back to M87. So the movie I showed are downscaled energies. They are downscaled by a factor of about 1,000. The energies are lower, but yeah.
Because you mentioned, for example, that you have some background soft photon field.
Mm-hmm.
So what's the density of this photon field, and into which object will that correspond to?
Yes. That's true. So that's a parameter in the problem. So that's why we have that's why we have the tau parameter that parameterizes the number density of this. This tau parameter parameterizes the number density of the photon field.
Okay, maybe we can let other people speak. So I can see Volodymyr is waving hand here for a longer time, and then Dimitri next. Volodymyr, do you want to ask a question?
Well, maybe it's a glitch of Zoom. No.
Okay, I can see your hand waving in Zoom, so maybe check this out. So, okay, Dimitri.
Thank you, Monica, and thank you, Alex, for the very interesting and stimulating talk. Really interesting, and I have tons of questions that I hope I will be able to discuss with you separately. But now, very quickly, I just wanted to ask, are there any observational constraints on the multiplicity in M87? So you're trying to produce some multiplicity, and you're saying that it's okay, it's not as high as in pulsars, it's maybe a factor of 10, but what should it be? What is the kind of goal? Do we know what it should be?
So on top of my head, I actually don't know what kind of observational. So
maybe
the only thing I can think of,
yeah.
The only thing I think of is that during the 2008 period of activity of the M87, there's a brightening of the radial core in M87. It's a slow process, so it happens slower that after we saw the TV flares. There was also X-ray flares from at the same time, but the radial come slower after that. So that could potentially, if that radial is due to this sudden new injection of pairs from this gap, then one could maybe estimate some kind of constraint on the multiplicity. We didn't do that. We haven't done that yet. But it looks like you need a lot more electrons than you can produce in the gap.
Okay. Thanks.
Dimitri, do you have more questions?
I do have
you can ask now because there's no other. Just go ahead. Yeah, go ahead.
Thank you. So I would like to understand, do I understand correctly that, okay, when you produce, so when the electrons are accelerated by the electric field at the gap, they're accelerated along the magnetic field lines, yes, right? And so they emit photons that also travel along the magnetic field lines.
Yes.
Is it true that the mean free path of these photons is much smaller than the radius of curvature of the field lines, the mean free path of these photons to pair creation? And so when they pair create, they're still traveling mostly along the field, and therefore, so it's a long sort of chain of arguments or questions, and therefore, when they produce a pair, the pair particles also travel along the magnetic field and therefore have small pitch angles, and therefore would not be expected to produce much of synchrotron radiation. So the question is, would you expect synchrotron radiation from?
That's an excellent question. It's also one of the on the roadmap thing that we want. So you can quantify that definitely. And although there will be small pitch angle, it would be non-zero pitch angle. And the pitch angle will be defined by the optical depth, but the optical depth is basically the system size divided by the length free path.
Do you mean free path, right?
Yes.
Yes.
So
and the system size is probably comparable to the
probably comparable to RG. So one could actually, this is a good exercise to do. I mean, this is one of the items that I should probably put on this one of the next steps that I can do is to get the synchrotron spectrum out of this, because they definitely will radiate synchrotron. The small pitch angle from the secondaries will very quickly radiate away this synchrotron energy, and that will come to maybe X-rays. Maybe that'll probably be one of the reasons that we see X-rays.
Lots of interesting things.
All right. Maybe since Chris? Yeah.
Yeah, just a quick question. So if I'm just an ideal MHD person, in summary, is there like kind of a first order thing I could do to incorporate any of this into such a simulation? No, like we know we're getting this region wrong in our simulations, but is there anything we could feasibly do to make it less wrong?
My immediate answer is it probably doesn't matter. No, so this probably doesn't really enter the MHD, because the density flow is so much higher than all the densities we're talking about here. So it probably doesn't really come into play.
And I know there's been some attempts to use this sort of thing to justify our density floors producing mass in the region, but is that just, are you saying it's too discrepant? Like, you know, the mass our codes is producing is way more than you're ever going to get?
It seems like the kind of gap will produce less mass than the usual density floors in the simulations, but I don't see why that will lead you. So I don't see why that is a problem in itself, because it's a low density region, unless you.
It probably won't feed back on the dynamics of the rest of the thing, but if we wanted to say something about like the Lorentz factors in our jets, right? We'll get the jet energy right, but because we get the mass so wrong, we'll have the.
I see.
Yes, precisely.
Yes, that's.
And actually, so Alex, you rather confidently said that the pair density that you're producing through the gap is much lower than the density floor. That implies that you know what the numbers are. Can you tell us what? Actually, this is Chris's question, I guess, right? How big is the discrepancy, right?
Okay.
What is the density floor and what is the density?
I probably should. I was too confident because I don't have the numbers.
I can answer this. It's huge density gradient between pairs in the funnel and the whole other accretion disk, whether we talk about Sagittarius or M87, and this is something that we cannot really handle with any of the codes.
No, but I mean, how huge? I mean, is it a factor of 1,000,000, 1,000, 10?
More than 1,000,000, I would say. It also has some radial dependency, right?
No, sure, but roughly speaking.
Yeah, it's like several orders of magnitude.
Okay.
Yeah, so it also depends on the radius. It's like 1,000,000 or something. Yeah.
Okay. So I'm not even asking about an order of magnitude, but like whether I should use kilo, mega, giga.
Okay. It's also model dependent, like we love to say it. So it depends also on the model, you know, whether it's M87 or Sagittarius, whether it's MAD or SANE. So, you know, I cannot give you the exact number, but, you know, it's several orders of magnitude.
Okay.
I would say that, you know, if you also said that it does not affect the dynamics of the rest of the flow, but, you know, probably something is happening at the surface, at the boundary, right? Something might happen at the boundary of the jet core and the jet sheath, right? If you have such a low density fast core and a slower sheath made of different type of plasma, then probably I would expect that there will be some extra shear, yeah? So in some sense, you know, saying that it does not affect dynamics, it's a little bit oversimplification.
Okay.
Thank you.
If I may comment on Chris's question, I think you can switch to like a force-free prescription in the jet if you were to couple everything, like, and it would numerically work, so that you actually are at infinite magnetization, which corresponds to Alex's initial condition, sort of. And then you could evolve test particles in the force-free field. So that far you could get, but you could not mimic the pair production. For that, you really need a kinetic simulation, in my opinion.
Right. I guess that actually kind of points out, in our ideal MHD, there's two limits here. There's the fact that around 10 to the 6, 10 to the density contrast, you just start not trusting things. Adjacent cells are that different. But there's also, most codes have a sigma limit of somewhere around 100, give or take a factor of 10. So there's that as well. But like, I guess the ideal, the force-free can get around the sigma limit is what you're saying.
Yeah, but then you don't have, if you are in force-free, you still don't have information on your temperature, density, and pressure. And right. Like your test particles would evolve according to the magnetic fields, which are maybe trustworthy and force-free, but you don't have any feedback of those particles, and you don't have any pair production, and you don't have any photons, etc. So I think it would be, it's completely not catchable within MHD models, the kind of things that Alex is doing. And
oops, I think we lost Bart.
Bart muted himself.
Please. No, Bart is here.
I'm here. I'm here.
Oh, okay, sorry.
Okay. Yeah, he's here.
Oh, okay. So, Alex, I would like to thank you maybe for your talk right now. Thank you very much. And thank you for answering all the questions. Bravo.